Swayam Prabha. Digital India. Educated India.
We are basically splitting this matrix along by the projection matrices, lambda 1, lambda. So lambda 1, lambda 2, lambda n are the components. Okay, we are not yet multiplying with another vector to get the projection vector or the length of the projection vector. That we are not doing. So these are the matrices. So we are breaking our main matrix into the projection matrix, the sum of the projection matrices. This lambda 1, lambda 2, lambda n are giving the importance of which direction we are having the maximum projection. Okay, so we are splitting our the main matrix by A by this diagonalization into the sum of the component projections along each of the orthogonal matrices, orthogonal eigenvectors, right? Now, I think in many applications you will see this. This is a square matrix. We will also come for the rectangular matrix because mostly our application problem will be coming in the rectangular matrix. But if you give some order this lambda is from the decreasing order, right? If you order this lambda is into decreasing order, and if you discard some of the things where lambdas are very small, so that will not affect our A that much. So it will be a good approximation. If you just consider the first few where the lambdas are very big, so those will be the dominant part in our matrix. So by that way, we also do some applications in image compression, or where we want to because these PIs are easy to store because in the computer memory, because these are rank 1 matrices. So there are advantages of using these matrices, and we can discard some of the things if we do not require. So that way we can compress our original very big matrix into this form. Okay, so there are a lot of applications we will see in other domain. So this is the idea we also want to extend for the general M by N matrix. Okay, you can try those examples, how to diagonalize a symmetric matrix, and you just verify that those are the orthogonal matrices, orthogonal eigenvectors you will be getting from those matrices, the symmetric matrices. Okay, now we'll come to the main part. So far we are just trying to understand what is happening in the square matrix. So that we can extend that idea, because unless we understand the square matrix, eigenvalue, eigenvector, symmetric matrix, we cannot go to the singular value. So what are the problems we have faced when we are working with the eigenvectors? First of all, you can see that the eigenvectors in general for a matrix, even if it is not symmetric matrix, they are not orthogonal. Okay, so orthogonality is a nice property we want to use, because we have just seen in the last slide how nicely we can project into the orthogonal direction, so that we can decompose the matrix in a nice shape. And another problem we also have seen with the eigenvectors, that there are not all the time there are not sufficient number of eigenvectors, right? So some of them, I mean, we can have less number of eigenvectors. Using that, we cannot diagonalize them, right? That is not enough number of eigenvectors. The third is that we need always square matrix. That's the most kind of bottleneck. To compute the eigenvectors, we always need a square matrix, which is not the case all the time in the real application. So you can have any dimensional matrices. So what we propose, we want to use, instead of eigenvectors, the singular vectors. So that's the idea of singular value decomposition. Instead of eigenvectors, we want to use singular vectors. So what are the singular vectors and how to compute them? So first, one observation you can also prove it, that first two properties. If A is an M by N matrix, now we are considering M by N matrix, not N by N matrix anymore. So we are considering M by N matrix. So then A transpose A will be N by N, right? A transpose A will be N by N, and this will be a symmetric matrix. A transpose A will be a symmetric matrix, and of course, whatever the properties we have seen, it is orthogonally diagonal. The symmetric matrix. Similarly, we can also consider A transpose, which will be an M by N matrix, which will also be symmetric and orthogonally diagonal. Okay. So, is it okay to check this property is okay? This will be symmetric matrix. Now, the second property is very important. So, if V1, V2, Vn be orthonormal eigenvectors of A transpose A corresponding to eigenvalues say lambda 1, lambda 2, lambda n, then lambda I is the length of this vector AVI square. How to check that? So it's let me try to prove this. If V1, V2, Vn be orthonormal eigenvectors corresponding to eigenvalues lambda 1, lambda 2, lambda n, then lambda is the square of the length of that AVI. So length of this AVI, right? That's what I am considering. This length. How we can write this as? Can you write this AVI transpose AVI? Okay. So this will be your VI transpose A transpose. You know this, right? A VI. What was there? Let me check that. So V1, V2, Vn are orthonormal eigenvectors of A transpose A. So if Vi is an orthonormal eigenvector of A transpose A, then what we can write? Vi transpose, this is equal to some lambda I into Vi, because we know that A transpose A Vi equal to lambda I Vi, because this is that equation we need to satisfy. Okay. So this is equal to what? Lambda I, and we know that this is Vi square. Is that okay? So this is what? Because these are orthonormal vectors, so these are of unit length. Vi is are orthonormal vectors of A transpose A. We can write this is equal to. So this is a nice property we need to use in the singular value computation. So now, so we define that the singular values of A are the square roots of the eigenvalues of A transpose A. Square roots of the eigenvalues of A transpose A. That is lambda is, and lambda is are AVI square. So singular values are the length of vector AVIs. So vector AVIs, then you take the length, these are the singular values. And the eigenvectors of A transpose A are called the singular vectors. So corresponding to the matrix A, we are considering A transpose A, finding all the orthonormal eigenvectors of A transpose A, and the singular values will be the lambda to lambda n, which are actually the length of those vectors, right? The length of those eigenvectors, orthonormal eigenvectors, and eigenvectors are already obtained from this A transpose A. So these are our singular values. So we will not be considering directly some vectors associated with A, but with A transpose A. So these are our singular values or singular vectors. The eigenvalues of A transpose A are the singular values. Eigenvectors of A transpose A are the singular vectors. Okay. Now we will be, but we are always able to find those n corresponding to this A transpose A. We are always able to find this n orthonormal eigenvectors, right? So that's the advantage of using the ATAM. So now we want to find that mapping, because we need the mapping, right, from that Rn to Rm. So if we are having this orthonormal set of eigenvectors here and orthonormal set of eigenvectors here, we need a mapping between them. So for that mapping, this property is important. So suppose V1, V2, Vn is an orthonormal basis of Rn consisting of the eigenvectors of A transpose A. Those are the singular vectors of A, right? So that the corresponding eigenvalues, now we will also order the eigenvalues. So it is like I was saying that you have to order in terms of the importance. So that's why we order always, we order the eigenvalues in the decreasing order. Okay? And we consider this V1, V2, Vn in that particular order according to this order of the importance of the eigenvalues. And as we know that not all the lambdas are positive, it could be also 0, right? Some of the lambdas could be 0. So if we order it, say our first R eigenvalues are non-zero and rest are all zeros. Okay, so that will actually depend on the rank of the matrix A. If we have the rank R, of course we will have first R will be independent, corresponding to that eigenvalues will be non-zero, and for others it will be 0. Okay, so that we will see. Suppose A has R non-zero singular values, then this set AV1, AV2, AVR is an orthonormal basis of the column space of the matrix A. Is the column space of the matrix A, and rank of the matrix A is R. So basically, if you see now what is happening, you have to go back to that picture. Finding this V1, V2, VR. So we'll be also having this orthonormal set of eigenvectors corresponding to VR plus 1 Vn. These are the singular vectors of A transpose A. Okay, so n set of orthonormal eigenvectors, and we have this corresponding to this AV. We want to find the mapping of, this is my row space of A, this is my null space of A. We have to show this. This is my column space of A, and this will be my null space of A transpose. So we have to find the mapping, how this V1, V2, VR are mapped to the column space of the matrix and the left null space of the matrix. So that's the you can see from this. So if we order this in the decreasing order, say last n minus r values are 0, then we can say that, so this set is the orthonormal basis. How to show that this set, one set of vectors, is orthonormal basis of the column space. So what are the properties we need to show? First of all, we have to show that the 3 properties we need to show. So these vectors are orthonormal, the first property. So I think that is clear. So that you can just check from the first line of the proof. If I not equal to j, then you just expand this, and then since vi, vj are orthonormal, then this will be the 0. The first line is clear, right? So these are orthonormal. This AV1, AV2, AVR are orthonormal. You take any 2 vectors from this set, you just multiply them, right? The inner product or the dot product, and you just see that this is the dot product is 0, so they are orthonormal. Now the next thing is that we have to show that to prove that this is the basis of the column space, what we need to show? Prove that basis. So two properties, right? Linearly independent, and it is also spanning that column space, right? So linearly independent, and also it is spanning the column space. So the second linearly independent. How to prove the linear independence? The column space. Yeah, that will come. But we need to use this property also. So you can just take these two properties there; they will be satisfied. So first, you just take a linear combinations of this, and then you can show that this will be a linearly independent set. Why? Why we are not? First of all, if we consider this n vectors v1 to vn, so what are these a v1, a v2, vn2? So these are the so the last n minus r avis will be, the length of them will be 0, right? Because this lambda is are actually the length of avi, right? So when we are saying that some of the lambda is at 0, because we are getting those eigenvalues as 0, so that means that avi is also will be 0, right? 0 vector, and so those we are discarding. So we have only the non-zero these APIs now, and it is easy to show that these are the linearly independent. And at the same time, we can also show that, so you can take any vector from the column space of the matrix A. Say we are taking that vector y. So corresponding to this y, we'll have some x in the row space, so that a of x is equal to y. A of x is equal to y, and we can show that this y you can express as a linear combinations of these AVIs. So that means that these vectors AVIs are actually spanning this column space. So the linear span of these are actually so basically the idea is that we first compute the orthogonal eigenvectors corresponding to a matrix A transpose A, and then the AVIs corresponding to this will be going to, AVIs will be going to here. AVIs, AV1, AV2, AVR, right? Now this is the 0 vector here, this is the 0 vector here. So all others, if you just all others will be going to 0, because this is the null space of this. They will be falling into the null space of the matrix A. So because of that property, so these will be the 0 vector. So we have now we want to express these AVIs using some formula, which will give us the this singular value decomposition. Let's see that one the last next property that. So this is the final property for the singular value decomposition. If A is your m by n matrix with rank R, then there exists an m by n diagonal matrix sigma with B 0, and these are the all the 0 elements here in the rest of the entries. With sigma is are the eigenvalues, which are the square root of lambda is. Sigma is are the the singular values, which are the square root of the eigenvalues. So then there exists also this matrix U and the V, so that A is equal to U V transpose, U sigma V transpose. So as you can recall now with the what we did for the square matrix diagonalization. Similarly, if you now use this property, what we have already proved, that what is your ui? So we consider ui, which are the AVIs, and we just make this unit length, because we need orthonormal set of vectors. So what we do, instead of this, we also divide this by norm of AVI1, norm of AV2, norm of AVR, right? And then our mapping will be, so we write this as ui, which is equal to AVI by norm of AVI, which is equal to AVI. What is this? This is sigma, right? So this is the this is the singular value corresponding to the ith singular value of the matrix A transpose A. So now, if we write this in this AVI is equal to sigma AVI, same way like we expressed for the square matrix, we can write A into V1, V2, VR, U1, U2, UR. So this matrix, so and into this capital sigma is here, not this one, but the part of capital sigma is the capital D is your sigma 1, sigma 2, sigma R into this. So this is the part of the singular value decomposition, but we have to. So here A is dimension m by n, but this matrix V1, V2, VR is n by R, right? Matrix B is n by R. Each V1 R. Matrix B is what dimension? N by R. So here this V1, V2, VR, if you consider this matrix, this is of n by R and this is of m by R, right? And this is dimension R by R. So what we need to do, we have to add few more vectors. We have to add few more vectors so that we get the complete square matrix of order n by n, m by n, and the diagonal matrix will also be of dimension m by n. So how to add? So what we have so far, we have added these vectors from the singular vectors of A transpose A, and corresponding to which we have got these vectors, right? We have added these vectors and this set of vectors. So this is also of dimension R. This is also of dimension R. So rest n minus R vectors and m minus R vectors we have to choose, so that they form the complete set of orthonormal bases here, complete set of orthonormal bases here. Okay. So for the null space of the matrix A, we can directly choose the VR plus 1 to Vn, because they are already orthonormal set of vectors, and they also will be the basis of the this null space of the matrix A. Okay, because they will be mapping to the zero vector in the column in Rm. Okay, but one final thing is left for the left null space, how we should choose the vectors, because none of the vectors are actually going to this left null space. So the vectors, the first R vectors are going to the column vectors, and the last n minus R vectors are going to the zero vector. Now how to choose the vectors from the for the left null space? Then we'll have the complete set, and then we also form the this U matrix also complete. So for choosing the vectors from the left null space, we simply so there are two methods. One is that you directly compute the orthonormal set of eigenvectors for A transpose. Okay, we compute the orthonormal set of eigenvectors for A terms, because left hand side is the singular vectors for the A transpose A. Similarly, right hand side are the A transpose. So we can from there we can just select the last set of vectors which will be coming into the left null space of the matrix A. Or you just choose, you just solve this equation, null space of A transpose equal to, you just find the basis vectors for null space of A transpose, and then you will be getting a set of independent set of vectors which will be orthonormal to this set of vectors in the column space. And also at the same time you have to do Gram-Schmidt orthonormalization process to convert them as set of orthonormal vectors. So you need both. You need to apply Gram-Schmidt method, at the same time you have to solve this A transpose y equal to 0 vector to compute the set of independent vectors. First you compute the set of independent vectors, then Gram-Schmidt orthonormalization method. Whenever you will find this set of orthonormal vectors, they should be always orthonormal to the other set of vectors because of the property of this they are orthogonal complement of each other, right? From there we can immediately say that these are the other set of vectors which are orthonormal. So that is little bit you need computation, but the rest of the things are coming directly from the A transpose A equal to the singular vectors of A transpose. Okay, so similarly, as we have said that we can decompose the matrix A in case of the square matrix. So we are now having this full set of vectors V, which will be our for the second line there is some typo. I think U V are just interchange. Please check. For the second line, it should be AV equal to U sigma. AV is equal to here. So I just corrected. AV is equal to this should be U sigma, and then we can, since this is normal columns, so this is the orthogonal matrix. We can take the transpose to write it A equal to U sigma V transpose, right? Equal to sigma V transpose, and finally we can write this as U1 sigma 1 V1 transpose, U2 sigma 2 V2 transpose, UR VR E sigma VR transpose. Now what are the matrices here? The last line, these matrices. These are again. So we are multiplying a column vector with a row vector. We are multiplying a column vector with a row vector, right? And that will be rank 1 matrix. Rank 1 matrix. What will be the dimension of these matrices? So U1 are from the columns. So U1 are coming from the of dimension M, right? M cross N. So it will be of dimension M cross N. So you just check that these are the rank 1 matrices again, and so these are the rank 1 matrices and will be of dimension M cross N. Okay, because our matrix A is of what dimension? M cross N. The matrix A is of rank dimension M cross N. So as I was saying that we have already ordered these sigma i's into decreasing order. Now we can again compress the matrix by discarding some of the entries in the end to just preserve the main important features in the matrix, right? So we can just take, say, first 2 entries and all the other entries we just discard, because the sigma i's which are more important, they will be preserving the important part of the matrix. So that's the idea they use in the image compression, in many techniques in image compression. Okay, so we have those properties of the orthonormal corresponding to the orthonormal eigen vectors. We have this V transpose V equal to In and U transpose U equal to In. So you can just verify this. So this is the singular value decomposition corresponding to a matrix for general matrix. Okay. So this is the last part of the fundamental theorem of part 3. So we are getting basically we are now choosing the set of orthonormal vectors from the for the row space, for the left null space, for the null space, for the column space. So so that we have discussed that how to compute that. So computing this this orthonormal set of vectors is actually the part of computing your singular value decomposition. Once you are able to compute it, you can I think I will ask the TA to give you at least one problem to solve because I don't have time to discuss the problem. You can just try yourself. So first thing is that first step you compute A transpose A. Second step you compute the eigenvalues and eigenvectors of A transpose A. So that is giving you the full set of the first R and also the this n minus R vectors. You are getting the complete set of eigenvectors. The third step, you apply this AVI, which is sigma I, right? AVI, you just multiply with this the singular vectors VI's with the matrix A, and you get the UI, sigma I into UI, right? So from there, you get the full set of U's, and the last set of U's, which will be in the left null space, that you have to find by solving either A transpose Y equal to 0, or you just compute from directly from A transpose equal to. So you can compute in either way. Both will be same. Both will be same. Okay, you need to practice how to compute this. There are a lot of steps involved in computing the singular value decomposition, but you can see that. Okay, so we can decompose a kind of the first matrix here is a rank 1 matrix, 2, 2, 1, 1. So it's a rank 1 matrix, and the other one is it's a rectangular matrix. Okay, using this concept, what we have just got a mapping between the the orthonormal set of eigenvectors in the in Rn to Rm, right? 4 fundamental subspaces. We can define the inverse of those mapping. SVD is actually giving me AVI is equal to sigma UI. So that's the mapping, right? So here I am considering the matrix A. As a linear transformation. If you are familiar with linear transformation, so you are taking a vector from your domain Rn, and you are getting a vector in Rm, right? So that's our mapping, and we know that corresponding to a linear transformation, if we know the images of that linear transformation corresponding to a basis vector, then we know that linear transformation completely, because we can then compute that linear transformation corresponding to any set of vectors in this space. If we know the images of the basis vectors, then we know the linear transformation completely. So to find the inverse, what do we need to know? We need to know the inverse of the basis vectors in the column space and the left null space. Okay, so that is how. So here the idea is that when we are able to find the inverse of a matrix, when it is non-singular, right? But when the matrix is say suppose singular matrix, or it is a rectangular matrix, we don't have any clue what actually should be its inverse. So here the pseudo inverse is actually generalizing that concept for a singular matrix or for a rectangular matrix. And this is coming from that our whatever the details we have seen, that how we are kind of finding the mapping for a SVD, for the singular value decomposition. You just consider the inverse of that. So now I'll show the picture in the next page. Now our mapping is here. So I will be denoting this A inverse by A plus, because here we cannot use that inverse, because this is the most of the time the matrix we will be considering are not singular. So it's a general matrix. Yes. So this is the technique of how to compute your. So first define. So this A plus is your inverse mapping or inverse linear transformation corresponding to the mapping A, and we will be defining in this way. So you'll be getting, then if you do little bit computation, you will see that you can write A plus as a similar way like we have defined the SVD. You can write it B sigma plus U transpose, and it will satisfy most of the nice properties of your invertible matrix, like A transpose A inverse equal to A inverse A equal to IN was there, right? The identity matrix for the non-singular matrix. Similar property. I am not saying exactly the same property, but similar properties will hold, and that is a reason that why I am talking the pseudo inverse. Just I'll take 5 more minutes. So you can compute the pseudo inverse by using this formula. So you just use compute the same way. You compute the singular values for A transpose. You compute the U matrix, compute the V matrix, and you compute sigma. Sigma plus will be according to this. This, if you write it in this way, it will be the sigma 1 inverse, sigma 2, sigma r inverse, 1 by sigma 1, 1 by sigma r. Okay. Yeah. So it will, because this from this relation we have this di by sigma I, right? So it's just little bit different, but you are able to compute kind of the inverse. What you compute for the singular matrix, you can non-singular matrix, you can compute a similar kind of inverse, which will be called the pseudo. Okay. So you just follow this formula, because you need to compute the singular values, singular vectors for computing SVD. At the same time, you can compute the pseudo inverse. Okay. So now I come to the last point, what we have discussed in the least square approximation. Right? We have done this when this image this AX is equal to B is not solvable. So you are projecting this into the column space, right? You remember? You remember that we are projecting into the column space, but there we had to solve a set of a normal system. That's what we told, right? Normal set of equations, which was A transpose A into X cap equal to A transpose B, right? That was your set of n by n equation, or n by n, or m by n, m by m equation, set of equations. Just a set of, so that was a square system. So we are able to that was the idea. So we assume, what was the assumption there? Why your A transpose A was invertible that time when we started with least square approximation? Can you remember? Can you recall why I took one assumption there, because of which I was able to compute the I was able to solve those system uniquely, linearly independent. Those column vectors of the matrix A were linearly independent. So when that is linearly independent, that means that our null space is only the zero vector, right? Our null space here is the only zero vector, and this will have this X cap. It was always unique there. our X cap, what we had computed for the this line fitting or parabola fitting or the kind of the least square approximation, whatever application we did, we assume that our column vectors are linearly independent, and that is why we are able to solve it. But in general, the column vectors may not be linearly independent. Then how to compute this inverse if that is not invertible? Pseudo inverse. Now we'll be using the pseudo inverse. Okay. So when the column vectors are not linearly independent, so this null space of the matrix A is not zero vector anymore. So we'll have this bigger null space. We'll have this bigger null space, right? So whenever we compute, say, some X cap, so that X cap is not unique, right? That X cap is not unique. So you need to solve here. There are some properties involved here you need to check. So first of all, this is, you can prove that X cap is pseudo inverse A into B. This will be a solution of your that system. First of all, this requires some proof. So this will be your so basically when that kind of situation will come, when Ax equal to B is not solvable, you are basically computing a pseudo inverse B. Okay, and so this is the kind of the direct solution of Ax is equal to B. Even if A is not, usually if it is invertible, we can invert it. But since our matrix A is rectangular or having dependent columns, so we can just compute the pseudo inverse A into B. Pseudo inverse, you know that how to compute, and you can prove that this solution X cap X plus, this solution is of the shortest length. So that also requires another proof, but you can prove that. So this is actually, so because you can have multiple solutions when this null space, when the null space is not your the zero vector, you can have multiple solutions. We want to choose the best solution here, best solution X. So you can prove that this X cap, which is the coming from the pseudo inverse of the matrix A, pseudo inverse of matrix A, which you know how to compute. So that solution is the having the least length. Okay? The length of that this X plus will be the shortest. Okay. So now you know the technique that if your yes. No. Yeah. So this is general property. I mean, even this is general property in the sense that when your matrix will be invertible, you can say that your you can prove that this will basically reduce to your the ordinary inverse. No. The thing is that what you are trying to solve here, you are trying to solve that system of equations. This A transpose A equal to A transpose A equal to A transpose A into X or X cap equal to A transpose B, right? So now your that solution will not come in the row space or the null space. In general, it will come here. In general, it will come outside this. So one will be the projection which is there, X plus, and another one will be coming from the null space component. So among all those, so you can choose any vector from the null space and add that with that X cap, and you can just say that that is your solution. But you have to prove that that X cap, which is coming from the pseudo inverse of A, is the least having the least length. That's why that is kind of the best solution. Okay, because our in general this X cap will come from this Rn. Okay, so then we will have the two components. One will be in the in the row space, and one component will be the null space. So you can choose any component here from the null space. So that will be your solution of that system A transpose A transpose A into X equal to B, A transpose B. Okay. So that we are not directly haven't shown that picture here. So there is another picture which will be coming from for that particular system. Okay. Because there is another property that A transpose A having the same null space as the matrix A. So using that, you can show since A here, since this matrix A here having the big null space, which is non-zero null space. So for that matrix A transpose A also, you will have the same null space, because both the null spaces for the matrix A and matrix A transpose A are the same. So that is another property you can prove. Okay, using that you can prove that. So what I want to say finally, that this is your solution when you will have the dependent columns in the matrix A, and you can prove that property that this solution will have the list length. Okay. So you now know that all the techniques given a rectangular matrix or a singular matrix, you can decompose it into the rank 1 matrices, right? And using the SVD. At the same time, you can also find the pseudo inverse for the matrix when your matrix is a singular matrix or a rectangular matrix. And so when you will have the dependent columns, you can use this. Okay. Thank you very much for your attention.